Hello everyone and welcome to the CP-31 Sheet Solutions by TLE Eliminators. Today we'll be discussing the 1600 rated problem 6 round dance. Alright, let's navigate to the CP-31 sheet and let's open up the problem, right? Okay, so let us go through the problem and we'll then discuss the solution. So N people came to the festival and they decided to dance a few round dances. There are two people in each round dance and each person has exactly two neighbors. There are at least two people, right? So there are at least two people in each round dance and each person has exactly two neighbors. If there are exactly two people in the round dance, then they have the same neighbor on each side. Okay. You decided to find out exactly how many dances there were, but each participant of the holiday remembered exactly one neighbor. Your task is to determine what minimum and maximum number of round dances could be. Okay, and then they give some examples of round dances. Like for example, the cycle 1 2 3 4 5 6 1, and yeah, this is the this is for the example, this is the minimum number, and then the maximum number is 3. So you can, for this example, you can have like 1 is paired with 2 and who's paired with 1 again, so you can have up to 3 round dances, and that is the minimum and maximum. And for this test case, that's why the answer is 1 and 3. Okay, let us have a quick look at the constraints. N goes up to 10, 2 times 10 power 5. A of I goes up to n, right? So this is the neighbor, and the constraints pretty much make it clear that the expected time complexity, right? Always start the problem with expected time complexity. So expected time complexity should be around big O of n log n or big O of n, right? So we get this already. All right. We are guaranteed that sum of n does not exceed 2 times 10 power 5. Okay. So now let's actually break down what's going on in the problem. Let's take their example and see what it means, right? So we know that a round dance occurred, but each person only remembers like one neighbor, and we need to find the what is the maximum possible round dances which could have occurred and what is the minimum possible round dances which could have occurred. Okay, so to solve this, we are going to see through some examples and we're going to use some graph representations. All right, so let's try an example. Okay, and the example is 2 1 4 3 6 5. All right, so how do we represent this? What we're going to do is we're going to represent as a graph. Okay, we're going to represent this as a graph. Represent as a graph, where each node is a person and edge is between two neighbors. Okay, between neighbors means when they had like danced with that particular person as a neighbor. So between every two neighbors there will be an edge. Okay, between two neighbors. Okay, note that since like the way the dance is happening is that like there are at least two people in each round dance, right? And each person has exactly two neighbors, so we don't need to worry about a person having more than two neighbors. So it's going to form a graph which looks something like this. We have a, let's say there are these 5 people, right? So 1 2 3 4 5 6, right? And we can say that the neighbor of person 1, this is person 1, person 2, person 3, person 4, person 5, person 6. You can say that one known neighbor of person 1 is person 2, right? Because we have 2 and 1. Similarly, one known neighbor of person 2 is the person 1, right? So we get edges like this. Similarly, between 3 and 4 we get edges like this, and 5 and 6 we get edges like this for the given example. Okay, now how do we see the minimum number? Obviously the maximum number becomes evident since we can take these two people as a pair, these two people as a pair, these two people as a pair, and we get the maximum answer of 3, right? So the maximum part makes sense. The maximum is 3. How do we pair them up such that we have the minimum answer? Well, simply we can put all of them in one big round dance. We can say that the original round dance could have been something like this, right? 1 2 3 4 5 6, right? 5, 6. And now in this case, like 1 remembers his neighbor 2, 2 remembers his neighbor 1. Similarly, 3 remembers his neighbor 4, 4 remembers neighbor 3, 6 remembers 5, and 5 remembers 6. So this also is a case which satisfies the what we're observing here. So we can say that the min answer is 1, maximum answer is 3. All right. So let's have a look at some more examples. All right, let's have a look at some more examples. Instead of giving you hard numbers, what we're going to do is we're just going to look at some graphs which are possible. Okay. And in fact, before getting to the examples, we're going to think about this graph. Okay. So we are representing the problem as a graph where each node is a person and edge is between two neighbors, right? This is what we are representing the problem as. So very important. And basically we're trying to see what graphs could have generated this graph if we like forget one of the neighbors and we only like pay attention to some of the neighbors, right? Okay, so let's take another example graph. Okay, yeah, so obviously since there can be at most two neighbors, this will be only graphs of degree less than equal to 2. Okay, graphs of degree less than equal to 2. Also, since each node is connected to at least one other node, also degree greater than equal to 1. So it's a very special types of graphs which we are going to be seeing right now. Okay, so which hold these two conditions. All right, so now let us take a particular example. For example, let's say we have like 8 people. Let's say we have 8 people, and let's say 1 and 2 are connected, 2 and 3 are connected, 3 and 4 are connected, 4 and 1 are connected. All right, then let's say we have 5 connected to 6 like this. Then let's say we have 7, 8, or let there be like more than this people. Let there be something like this. Okay, yeah, so we have something like this. Okay, now how do we see what is the maximum and minimum number of groups that we can form? All right, so the first observation which we can have for a graph like this is that we need to make them form into groups, right? So the first observation which we can have for a graph like this is basically if we already have a fixed cycle, right? If we already have a fixed cycle like this, like we know that, let's say 1 knows that his neighbor is 2. Let's say 1 knows that his neighbor is 2. 2 knows that his neighbor was 3. 3 knows that his neighbor was 4. 4 knows that his neighbor was 1, right? So we already have a given cycle. We cannot break this cycle if we cannot connect 3 to 5, because we can have at most 2 neighbors and we already know which are these 2 neighbors, right? So basically for all cycles of size cycle length or cycle size greater than 2, right, or greater than equal to 3. So basically 2 cycle does not count, since it could just be one neighbor. It does not mean both side neighbor. But as soon as we have a 3 size cycle or a 4 size cycle or bigger, then we know exactly that this guy was this guy's neighbor, this guy was this guy's neighbor, this guy was this guy's neighbor, and this guy was this guy's neighbor. So basically for all cycles of size greater than equal to 3, they form a round dance, right? They form a round dance. They form a round dance, and this dance cannot be merged. This dance cannot be split or merged. Cannot be split or merged with the other let's say connected components, right? So I hope you know that by 16, when you're solving 1600 problems, I'm expecting that you already know what a connected component of graphs are, right? So basically connected components are the graphs which are like reachable, the nodes which are reachable from a particular graph. So for example, this would be a one connected component, this would be another one, and this would be another one, right? And the thing is, so we cannot merge this with any of the other connected components, and this is the first observation that we made. All right, moving on. What else can we observe? What about the other two? Let's say we have a connected component like this, 5 and 6, right? So let us call these cycles. So the ones which we can't merge are called cycles. Now let us see our attention to the other ones, 5 and 6, and then we have 7, 8, 9, and let's say 10. Okay, obviously this can't go on forever, it has to stop at some point, right? Otherwise it would become a cycle. So what can we do about these, right? Obviously if we keep them separate, we are maximizing our answer. And what happens if we try to merge them? Okay, so what happens if we try to merge them? Well, 7 knows that one of his neighbors was 8, right? 8 knows that one of his neighbors was 9. 9 knows that one of his neighbors was 10, right? And 10 also knows that one of his neighbors was 9. But what we can do is, like here, this is a cycle of length 2, right? So basically we just know that one of the neighbors are fixed. So what we can do is, we can assume that, let's say 5 was the neighbor of 10 and 6 was the neighbor of 5. Okay, so basically if we form a cycle like this, then we have successfully merged, right? There is a scenario, there is a scenario of successfully merging two non-cycle cases, right? Two non-cycle cases. And this is how we're doing it. Basically we're saying, okay, we had like basically 10 and 9 be neighbors like this, right? So double relationship between 10 and 9. We can open that up and we can say, okay, 10 could have been connected to 5, 5 to 6 obviously, and 6 to 7. So if this situation was there, then we would have only one round dance instead of two, and it could still produce these two, right? It could still produce these two as the memories which remain for the people, right? So basically non-cycle cases, so we can call the non-cycle case either line case. There are many terminology for this. Either it can be called a line case, chain case because it looks like a chain, and sometimes it's called a bamboo case. So we're gonna call this the bamboo case because that's also very common terminology. So basically it looks like a bamboo, like a straight line. So for the cycle cases, for cycle cases, we have no option but to take it as a round dance, right? So we can't do anything about it, we can't touch it. For the bamboo cases, for the bamboo line cases, we can merge them together. Okay, we can merge two or more cases together. Okay, two or more cases together. Okay, so let me give you a quick example for this. So let's say yeah, so another example, let's make a few cycle cases first. Let's say we have 1 2 3 and 4 5 6 7, right? Then we have, let's say 8 9 10 11, and like this, and maybe 12 13 14, right? Something like this. We have a case, and then we have a case like we could also have a case which is like pointing both directions, right? So let's say we have 15 16, and these two know that they're each other's neighbors. But also let's say there's like 17 which knows that it's 16's neighbor, 18 which knows that it's 15's neighbor. Okay, and let's say we have 19 as well. So then we can identify that these are cycle cases, right? These are definitely cycle cases, right? These are cycle cases, cycle, right? And we can also say that these are the bamboo cases, right? These are bamboo cases. Bamboo. Why is it bamboo? Because it's like a straight line. I mean, this is not a cycle technically, right? This will just be like in a graph when you represent it in an adjacency list. This will be only counted as one edge, right? This will be counted as one edge basically if you represent it as an undirected graph. So this is the line or the bamboo case, right? These are the bamboo cases. Bamboo, bamboo, and bamboo. Now, the nice thing about bamboo cases is if we take these places where we have like this double edge, we can merge them with, let's say, we can have 11 as a neighbor and 10 as the neighbor, right? So we can merge them like that, and we can merge all the bamboo cases similarly. So basically what we have seen from this example and this intuition of seeing it in the graph form is basically, let me just summarize what we have seen. Summary: treat it as a graph. Each connected component will obviously be in the same round dance, right? Same round dance. And then cycle connected components. These connected components cannot be touched, cannot be changed, no matter what operation or basically what kind of simplification we try to make. But the chain or bamboo connected components, let's call them bamboo connected components, these can be merged until only one bamboo remains, right? Merged into one bamboo. Okay, and this is pretty much all we need to solve the problem. Some idea of how to see the graph in terms of connected components. So after this we can write a simple solution, right? Once we have made all these observations, and that solution is going to be the solution is basically going to be if no bamboos, then minimum will simply be the number of cycles, right? So let's call that C, and the maximum will also be the number of cycles, right? Now if there are bamboos, if let's call number of bamboos 0, B equals 0. If there are bamboos, so B is greater than 0, right? In this case the minimum will be C plus 1, okay, because we can merge all the bamboos into one, and the max will simply be C plus B, right? Because each connected component must be in the same round dance. So the max round dances will be C plus B. We never merged any bamboos together. Okay, so basically what is our goal? Our goal is find each connected component, check if cycle or bamboo, and increase C or B, right? Increase C or B according to this. And basically once we have the value of number of cycles and number of bamboos, we can simply print this answer, right? For minimum and maximum number of round dances. Round dances are basically connected components. All right, so that is the observations for this problem. How to find connected components? We can simply use DFS, right, to find connected component slash cycle or not. We can use DFS, or we can use BFS as well. Any path traversing graph structure works, right? And what would be the time complexity of this? Simply big O of n, because DFS on a tree this is not exactly a tree, but the number of edges is also n itself, right? So that's why type complexity is big O of n, as well as the memory complexity is big O of n. So if the idea is not yet clear, we'll have a quick look at the code, and that should clear everything up. All right, okay, so going to the code, we are globally declaring n, a visited array, as well as an adjacency list, because we need to do DFS, and this will be convenient for us. Okay, for each test case we are taking the input values and we are assigning it into the adjacency list, right? So basically by having x remember a neighbor, by having the node I remember a neighbor which is node x, it basically means that there's an edge between x and I, right? Which is what we're adding over here. Okay, now for each node, whichever is unvisited, we are going to do a DFS on it, right? We also want to know whether it's a cycle or not. And the simplest way to check for a cycle is that adjacency of each node will be 2, right? Adjacency of each node will be 2. So that's what we're going to do. We're going to do a DFS on I, which is going to mark this component as visited, right? And it's also going to mark the cycle, right? Whether the cycle is true or false, whether it's a cycle or not. We're also checking the length of the component, because if we have a cycle of length 2, then obviously we should not count that. That is simply a bamboo, right? Let us have a look at the DFS function. It takes the I, it takes cycle and length. It sets visited of I as true, it increases the length. If the adjacency is less than 2, then this is not a cycle, cycle equals false. And now we just continue by recursively calling DFS on the unvisited children. Okay, so this is basic DFS. The time complexity is big O of n for this DFS, as well as memory complexity is big O of n. Let's have a quick dry run. So sanity check in case we did not understand like what's going on. So let's do a quick dry run as well before ending this, right? So dry run. All right. So let's say we have the let's say we make our own example. So let's say we have array A equals, let's say 2, 3, 1, then 5, 4, then let's say we have 7, 6, and 6, 8. Okay, so now let's say this was our input, right? This was our input. So we're going to convert this into adjacency list form. So basically we're going to treat it like a graph. We have 1 being adjacent to 2 because 1 is a neighbor of 2. Similarly, 2 is a neighbor of 3 and 3 is a neighbor of 1, right? So we get this kind of thing. This is how we draw the graph or make the adjacency list. So basically 2 is the neighbor of 3, 3 is the neighbor of 1, and 1 is the neighbor of 2. Okay, now here we have 5 is the neighbor of 4, 4 is the neighbor of 5, so we get something like this, right? So we can just draw like this. Now we have 6 is the neighbor of 7, 7 is the neighbor of 6, 8 is the neighbor of 6, 9 is the neighbor of 8. Okay, so again we can just erase this part and we can draw it like a bamboo, right? So we can see that this is a cycle, this is a bamboo, and this is a bamboo as well, right? This is a bamboo as well. So basically, as we had observed earlier, we cannot really merge 2, 3, 1 with anything else. Like we can't have 2 be adjacent to 3, 3 be adjacent to 4, and 4 be adjacent to 1. Let's say something like this, because then we won't have 3 and 1 adjacency, right? And if we have like this, we can't have this because each node can have at most 2 neighbors, right? So we can't have something like this as well. So the cycle case is unmergeable. C equals 1. Now here we have one bamboo case and another bamboo case. Bamboo cases are easily merged. We can simply do something like this, and we have merged them into a cycle, right? A round dance basically. So for the bamboo case, we get B equals 2, right? We get 2 connected components which are bamboos. So the answer for minimum will simply be 1 plus 1, right? Because 1 cycle and 1 bamboo, because we have merged them, there'll be 2. And answer for max will again be C plus B, so that will be simply be 1 plus 2 equals 3, right? So that's all for the answer to this question. Go through the code once if you didn't get it, right? The idea is a common idea of for example graphs of degree 2. The idea of splitting into cycles versus lines or bamboos is pretty common. If you struggle with this question, then here are the topics you need to focus on. The topics was DFS, BFS, graph observations, and maybe a bit of like, constructive skill or a greedy skill basically, to know that this is how we minimize and this is how we maximize, right? So we need some basic constructive ideas. All right, that's about it. Let's just go through the code. Like, we've already gone through the code. And yeah, here we're increasing C if it's a cycle, otherwise we're increasing the bamboos. If b is greater than 1, b is greater than 0, that means there is at least one bamboo. We can merge them, so C plus 1 is the minimum and maximum is C plus b. Otherwise, in the cycle case, both will be C itself, right? So that's all for this. If you have any doubt at any point, I highly recommend, taking pen, paper, take notes, rewatch the video. That usually clears most of the doubts up. And yeah, that's about it for this question. Thank you for watching and see you in the next one.